I think. Okay, it should be good now. Okay. I'm clicking on more names. Okay, I clicked on a lot of names. Okay. Well, where's my notes for today? I think this is going to work. All right. We are at 2 o'clock and 2 minutes. Good afternoon, everybody. Are you ready? I'm always supposed to make an announcement first. What's our announcement? You know what it is. No one knows. That's too bad. Poor Johnson's going to feel so disappointed. You forgot all about him. Okay, I'm going to switch the camera. Okay. Oh, you know what? It's not plugged in. I better plug this in. Where is it? Now I'm going to get it. So bad. Okay, camera. Just come live. Okay. All right. Okay. So good afternoon, everybody. You know which announcement I always make first, don't you? On Tuesdays and Thursdays. You're all abandoning poor Mr. Johnson. Johnson teaches supplementary assembly program at 5:15 today. Okay. Every time somebody fails a class, I ask a few questions, and then I say, "How many SIMEs you attend?" Oh, I didn't need that. That would just ruin my whole day. Well, now you know why you got such a low grade. So don't be one of those from the past. He's a good guy and he knows how to get your program done, especially number 3, which we'll talk about at 3 o'clock. Okay, so back onto agenda. I'm going to go over some things that I kind of talked about already, but if it sounds familiar to you, just hang on. It's needed by somebody else in the classroom, and so you might hear some things twice. If this is a repetition from last class meeting, you still need it. Okay. I'm looking for my, I'm in tool chains. I lost my, well, no, that's not it. This is close enough. Okay. The goal is here that you know all the parameters of that are used in bash files. All right, so when we're compiling C++, it looks like G++. Let me see if that shows up in the middle of the screen. I think it does. G++. And you're supposed to know all, the meaning of all that follows. C, M64, wall, std equals C++ 2a hyphen f no pi hyphen no pi hyphen o quadrilateral dot o, and then one more is quad dot cpp and hyphen g. Okay, so let's make sure you know what all those pieces are. They're parameters to this function over here, which is to compile something. Okay, and then let's take them one at a time, not spend too long on each one. Hyphen C means compile this only. The only is important. Compile only. And then it means avoid any linking with library functions. If there's include files at the top, it doesn't do anything with them. It just compiles the existing file only. And the existing file is this one here. Okay. And because these can be put in any order, except these two have to stay together as a pair, they can be placed in any order. This compiler has to figure out which ones belong to which. I think that's probably easy. There's only one lowercase c, and there's only one of all this other stuff, but it figures it out. Okay, so what is the opposite of compile only? It's big S. Could be a replacement for compile only, and that means output and the assembly version of the input file. Okay, so the input file is here, underlined in red, and the output file is up here in the box. And if you use the uppercase S, then this file that's in the box comes out in all assembly language. It's a translation from C++ to assembly. But didn't I tell you last class meeting that there's two kinds of assembly? There are two syntaxes for one language. When we just say x86 assembly, there's one programming language, but there's two syntaxes. Okay, so if it's hard to come up with here. I use Russian language. If you write Russian language in Cyrillic alphabet, you're using one syntax for Russian language. If you write Russian language in Latin alphabet, you're using another syntax for the same language. It's read and pronounced exactly the same in both cases. Is that how you spell syntaxes? Assembly has two syntaxes. The one we're learning this semester is called Intel syntax. What's the other one called? Anybody remember? It's the phone company. AT&T syntax. Okay. So online, if you web search for something you want to look up, I don't know, how to multiply two integers in assembly. And the answers they provide you, some will be written in this form and some will be written in this form. Yeah. And truthfully, I've never tried to understand the AT&T one. There's enough work to do just to understand the first one on the list. So if you get an answer online that involves here, I suggest you just pass by and go on to something else. Pass it by. Unless you have a lot of time and you're going to study for a month or so to understand AT&T assembly for the x86 processor, then go ahead. Most of the time, you just look at another entry from your web search and see if you can find one of those examples. You want to stop that? Okay. One language, but two ways of writing it, two syntaxes. That's what it's about. Okay, let's put that out of the way. What else do we want to know? Keep it, I think I talked about this, but let's make it absolutely clear. Pi means position independent executable file. Position independent. Pendant, A-N-T. Executable. Yeah. Why they have two kinds, I'm not fully certain. It belongs to another area of study, to operating systems. There are executable files that are of the type Pi, and there's others of the type non-Pi. The one thing I do know is that when you go to link object files, they all have to be of one kind. Either they're all Pis or they're all non-Pis. So the link command, G++ -M64 -std C++. What number do you like? 17. And finally, you come to the end, which is A.O, B.O, C.O, and -O, space my program.out. Okay, so the problem is if one of these, or let's say it differently, all three have to be the same kind. Either all three are Pi or all three are non-Pi. Okay, we can handle that. You can put in the execution statement, right there it is. In the compile statement, you can put F no Pi and just no Pi. As far as I know, they both do the same thing. They make sure that the output file here is a non-Pi. Or say we won't use it, but there's one that simply says make it a Pi. That's -PIE. Okay. If you put that in there, it guarantees that the output is a Pi type output file. Okay, so what does all this have to do with us? The problem stems, as far as I can tell, the problem stems from the fact that NASM only makes non-Pis. Okay, so one of these came from NASM and the others came from C and C++. NASM can only make non-Pis, therefore we have to force C and C++ to make non-Pis. And that's why in many of the examples online, in the bash file, you'll see one or both of these statements stuck in there. Okay, you all got it. So if I asked you on a test, why are we making non-Pi output files? You can tell me why. Okay, so what else is next on here? We talked about all the standards. Okay. std equals, and then you name your language. You could use C language and state the last revision. This is a real old one, C 1998. It would look like that, or you can do a more modern one, STD. I think there's a 14, C14. I'm not sure about 17. So every time the standard of what the C language is supposed to do is written into a book and it's labeled C standard 2020, or the same thing happens with C++. It's written into a book held by IEEE. I think that's where it's held. I take that back. I'm not sure where it's held. Okay, so it would look like C++ 2020 should exist, and it should look like this, but I've tried it and it says not ready. There's a message that says not ready, but there's a fill in for the time being that's C++ 2A, and that does work. And the one before that was standard 2017. Okay. And it goes back in history for the 20 years earlier than this, about every 3 years, 2011, 2008, and further back. Okay. So why do you need to know this? Because you're going to go to work in a place that's not an academic place where we don't care. You're going to work in a software development firm where there's lots of people working on a project, and the project is huge. This is the calling diagram. I'll stop here. Okay. And it goes on for dozens and dozens of more file modules. One team works on this piece, one over here, one works on this piece over here. Somewhere, everybody's got to get together and agree, we're going to use C++ standard whatever, and pick the choice for this project. And usually they'll go for the newest one, like year 20. And it will be told to everybody, compile with standard C++ 20, but our 20 doesn't work on our, well, you try it on your machine. 2A did work. I don't know why the discrepancy in naming. Okay, so in your employment place, where it's huge project to work on by dozens of people, somebody in higher management has to set the standard for that project and agree we're all going to use C++ 18 or some, whatever the number is. So now you know. What else is, let me see if any messages, yes. Okay. You know what wall is. I didn't put wall in there. I forgot it. Oh, I did put a wall. That means show me all the warnings. W is warning, all is just all. Show me all the warnings. This one means output for running on for execution on a 64-bit computer. You could choose -M32 if you had an old computer and you wanted it, and a 32-bit computer cannot run 64-bit software. The reverse is true. A 64-bit computer in legacy mode can run an old software. So if you wanted to create software that poor people in a third world country could use on old 32-bit machines, then you'd use this one right here. Okay, and you know what little lowercase c does, and you know about the two syntaxes, and you know about the pies, and we're almost there. One more. What is G? G is all by itself. G is the debug parameter. Most of the time you leave it out, but if you have a running program and you just can't figure out why a certain value is appearing wrong, then you want to go into a debug mode, and that means you have to attach -G in the compile lines, like I did here. And also in the linking statement, you have to put a -G. So it's, after your program works, you take the -G out. It is for debugging. For debugging. Okay, not yet, but in a few weeks, we're going to do that in our programs. We're going to insert the -G parameter, and then it enters a debug mode under control of the debugger known as GDB. Okay, that's the piece of software that lets you see values in your registers before the program ends. While it's running, you see what's in different registers. So a debugging program. No, it's a debugging add-on. Okay. It temporarily converts your program into a form that you can step through it instruction by instruction and watch the values in registers as the program's running. And then you can find where the wrong number gets in the wrong place. Okay. What else? Linking. It almost looks like compiling, but G++ linking, you cannot put a -C or a -S. -C in a linking statement doesn't make sense because that -C means compile. But you should put M64, and you should put your standard there. And you make a list of the O files, triangle.o, shoes.o, food.o. And then you have to name what will be the name of the executable, Mr. O, -O, final program. .out. Okay. So the S and the C have disappeared, and this becomes a linking program, a linking statement that combines all the O files into this one. Okay. You okay with that? Everybody says so out. You can put, yes, you can. You can put your name. I think that looked really nice. And it will run.
Professor, what is the M64 mean again?
The target computer is a 64-bit computer. For most of us, 99% of us walking around California, all of our computers are 64-bit machines. But there's parts of the world where they have old equipment, like Nepal. I read a story about people in Nepal have old computers from the 1990s that they still use. Okay, for them, you would put hyphen. If you want the program to run on their computers, you would put M32, -M32.
Thank you.
You're welcome. That's okay. In short, it means the target computer is a 64-bit one, and it organizes the output file in 64-bit mode, in 64-bit fashion. It uses the full power of 64-bit registers in the final executable file. Okay, let me see if I have any more. Are there any more assemblers other than NASM? NASM is a free of charge, open source assembler. But are there any others? Well, yes, the author of the ebook says he did all of his work on YASM. And I haven't seen it in a long time, but I remember some time ago there was TASM. T was for turbo. I wonder if they're still around. Anyways, there's 5 or 6 of these in the world. A couple of them cost money. Some others don't cost money, but this one seemed to be as good as any of the others. So I just picked that one. I could have gone with the one in the author used, but NASM, they're all complex, but NASM seemed to be the least complex of all of them. That's all I can tell you. Okay, there are others. You may end up in a job where they're using one of the others, but it doesn't matter. You already know what to do. Okay, let me see if I have anything else to give you. Pi SCS standards. Okay, and now I'm looking at my notes to remember if I did it all. I think so. That's about all. And last of all is, if you study bash files outside of this semester, they are very powerful. We're using simply the most elementary form of bash files, but you can put bash files and you can put into them loops that do looping. You can make if-else decisions inside of bash files. Do this if something is true, else do this other thing. They can be, there's a whole science in bash files alone. So, but we're using elementary bash files. So future study, not this semester. Okay, see if we got anything else. Any questions? Okay, let's go to, how'd the clock go? That was a half hour. Okay, I think I'm gonna switch topics, class. You ready? Let's pretend we're starting open lab time. Okay, so that means we study programming. In assignment, it's not assignment, in practice program number 3. Let's see, there's a top level, what assessor, ASSESSOR, accessor.com, not com. That's really dumb. .cpp. Okay, there's that file, and then there's one below it that's manager. .asm, and then that one in turn calls another program, which is just still in view of the camera. I hope it is. Down here, this one calls this one, and his name is fill the array. And then after this is done in the right order, this manager calls on show the array. Okay, and there's a third one over here, which we'll get to another day. We're getting close to approximating real commercial software development. They have a big tree of this stuff, but we got a little tree. And it's not always a tree. Sometimes it's a graph. See, one of these could call back to here. That's not a tree structure. That's some kind of graph structure. But it's legal. It could call back here to start something else. Anyways, let's look at these pieces right in here and see what we have to know. Okay, the assessor Well, this is a problem about the property taxes and how you're taxed on how much your property is worth and stuff like that. Okay. So assessor, you know what that is. It's an introductory message, call the manager, and then it's a goodbye message. This one is not involved in the solution. It's just a welcome, happy stuff. Not in solution. Okay, so 30 seconds we'll be done with it. The assessor, that's the file name, but it's main. Main says to us, says to the user, welcome. It calls manager. And it says goodbye. Okay, not much there. Okay, manager is a different story. This guy is like in a corporation. The manager is somebody important going on here. So this module manages all the other stuff. That's what it's supposed to imply. Okay, so this manager wants a list of property values in a certain sector of the town. Got the point? So manager declares an array that's going to hold floating point values that are somehow related to property values. We don't care how, but just imagine that. So array of doubles. Declared inside a manager. In manager. Okay, manager is, see the little attachment, the extension is ASM. It's written in assembly, but we don't care, you know, when assembly gets assembled into an object file and the equivalent in C++ gets assembled into an object file, the distinction where they came from is gone. Nobody knows it anymore. Whether that's C++ or assembly, it doesn't matter. After compiling, that's all gone. It produces the same file. So if that were C++, I would say property, let me try again. I'd say double property. $25. Okay. But translated from Greek to Italian, it actually comes out as property RESQ 25. It's just it's a matter of language translation. When this one compiles by C++, you get the exact same thing as when this one assembles by NASM. Okay, but let's make sense out of what is an array like property. Anybody can throw that out and start assigning values into it, but does everybody know what it really does? Okay. The name of the array is actually a number. It is associated, or it holds a number. The name of both of these of array is, or should I say holds, a number which is an address in heap space where there are 25 available quad words, comma, an address in heap which is the start, that address is the start of 25 available quad words they're not currently in use. So in heap where 25 words are available. Okay, I better draw a picture of that. Pictures tell better stories than 1,000 words. Somebody said that a long time ago. Okay, can we draw a picture of memory? Like so. Okay, so I said it was a number. Property is associated with a single quad word. Okay, I'll make up one. 6B 77A0. Okay. That's stored, and there's a table that says property as a word in source code is actually this number. Okay, that number is down here, 6B77A0. And I don't have room for 25 of these. There's 25 of these. Okay, so the next one right above it, 6B77A8. The next one above that, 6B77B0. And you count forward, getting higher, like I've been doing, until you get 25 total. And that's the array. It's split like that. There's a huge gap in the middle. A gap, GAP. Okay. So the name of the array is the number that matches down here to where there's available free space for all the members of the array. They'll be stored in this area. Okay, so we're going to come back to that when we do scanf on an array. We have to know these numbers are there like that. What else do we need to know? Okay, so don't forget the diagram. Okay, I should mark this up here. This is stack. This is the heap. And even very specialized, a sub-segment of the stack is an AR. Okay. All right, so now where's the diagram? The diagram said that manager has to call this function in another file and ask it to fill data into the array specifically from the keyboard. KB goes inward as the data flows in there, and this function is going to put the numbers one by one into the array and then send back how many numbers were inputted. Get sent back. Why don't I say the array is sent back? There's no need to. Manager already owns the array. Manager created it, declared it, and owns it. Just this guy happens to borrow it in order to put a few numbers in it, but the manager already has that. The manager doesn't know how many numbers this one is put in there. So as a return type, it should send back some kind of integer. Got that? Okay, so we're all great programmers. We can just write a prototype for fill array. Let's do it here. I just said it's going to send back a count of how many. Long fill array, parentheses. In order to put numbers into the array, the function fill array must receive access to it. So that would be double, comma, long, which do we need to give, that's the size. It's the 25 number when I wrote this. See the 25 numbers here, 25 numbers. So long size. Okay, that's the prototype for the function fill array. And it's the same whether the function details are written in assembly or C++ or C language. It's still the same prototype. So this prototype is good for assembly and it's good for the other two languages as well. All right, so manager has to call this one. What's manager written in? It's in assembly right here, right there. So let's make a setup for manager to call fill array. So he's going to call down here. Okay, we do it right here. So block to call fill array. Okay. The rule about RAX is that's the number of XMM registers involved. And we haven't got far enough into it, but I can tell you none of this involves XMM registers. There's no, in the coming yellow pages, there's no XMM registers. Therefore, we set this to 0. Okay. Next one. We're going to look over here at the prototype. The prototype says the next parameter should be an array of quad words. Double is a quad word. So let's do it now. Move RSI. I think I called it on the other page property. Okay. And then the function receiving this, the fill array function, is going to be called, but it needs to know how big is this array and how in the sense of how many cells are in this array. So let's move. You know what? This is a misprint. That's a D. Can you read that? It's really horrible. RDI. RDI. Okay. RSI is next. RSI, comma 25. There's the 20 that matches this second parameter. First parameter, second parameter. We got it all set up, and so we call fill array. Looks pretty good. Fill array does its work. It puts 17 numbers into the array, but it should tell us, hey, I only put 17 in there. That's this piece over here. This part of the prototype says this function is going to send back a long integer. Long simply means a 64-bit integer. Okay, so how is it going to do this? Fill array sends it back. It sends it back in RAX. RAX is a volatile register. We need to save that number. So let's do it right here. Move R15, comma, RAX. And now the block is done. It's accomplished its purpose. And a note on the side you should put is R15 equals number of values stored in the array. Okay. And I'm trying to get part of your assignment done for you. Just like this here. Okay. Everybody got it so far? You're good to go with it. Okay. Okay, so we're gonna go on. So this weekend, you'll make a lot of good programming progress. Okay, so here we are. See, manager is calling this one. And this one sent back in using RAX, it sent back how many numbers were in there. And this one then saved it in R15. See how it works. Now let's look at this one. That's more work to do. Okay. Let's keep this at hand. Start another page. Okay. What about fill array? Fill array. We already know it's prototype. It's, I won't dig it out. It's on the previous page. Fill arrays prototype. So here we have, I'm inside a fill array now. In fill array. Okay. Segment dot text fill array colon. Are we inside the light camera range? I think so. We won't write them. There's a lot of pushes here. Okay, we better go back to the prototype. Remember that manager is sending two things to fill array. Fill array's responsibility is to safeguard those. So right next thing to do after those 16 pushes is to take the two items that have arrived and save them. So here, let's do it. Make a copy of the first one. Where should we put it? I think I used R15 already. No, that doesn't matter. That's in the old, that's in the manager. R15 is in use. We'll do it right now. Okay, so move R13, comma, RDI. First parameter gets saved over here simply because RDI gets used over and over again, but R13 is less used. Therefore, R13 is a safer storage place. R13 is the array. It was RDI was the array, but we're copying it into R13. R13 is more secure than RDI. And then the second number was the size. Let's move R14 RSI. So the comment that goes with it is R14 is maximum number of quad words in the array. Okay, there's reminders nearby what it is. So we have keeping track of R13, R14. Okay, so I'm thinking we have to get all those numbers into the array. You ready for this? Let's pick a register that's going to be the index into the array. So R15 is a good candidate for that. Move R15 0. R15 is index of array. Okay, now I need to make a picture. We're going to write more source code here so you can get this whole function written up in the next day or two. But we need to pause for a picture because our goal is understanding as well as just getting some code written. Okay, so R13 holds a number. That is the array. Remember, the discussion 20 minutes ago was the name of the array, which is R13, is a number that leads to the first cell in that array somewhere in the heap territory. Okay, so this leads to, let me see if I want to change markers. If it's going to be any better. Let's try. Okay. So that's out of ink. That's a terrible one. Okay, let's try another one. Okay. Now this is in the heap. It doesn't look like it's stacked up in memory, but it's just drawn on its side where this much is a quad word, this is quad word, this is quad word, quad word, quad word. So, okay. In normal, for us humans, we like to think of it as this is number 0, this is number 1, number 2, number 3, 4, 5, 6, so on. But those numbers don't do the machine any good. This number here leads to an address, which is the address of the first byte here. What was that number in the past? I'll use the same one. Here's the picture from the past. 6B77A0. Okay. 6, in case you play back the video, you'll see 6B77A0. Okay. That's stored in R13. And in memory, every byte has an address. This address leads to the first byte of the first quad word of the array. And if we add 8 to it, so I'll draw the arrow in here. If we add 8 to it, 6B77A8 would be the first quad word, would be the address of the first byte of the next quad word. And so I'll run out of space pretty soon. The first byte in number 2 will be 6B77B0. Okay, so by adding 8s, you can find the true address of the first byte in the quad word. I'm trying to draw an arrow to the first one. Okay. Those are the numbers that scanf wants to know in order to place a number inside your array. And you're still with all this. Why do I? Okay, we need to explain scanf first. Scanf has a prototype. Every function has a prototype. Integer scanf %LF quotes, comma, and then if this is written in C++, you want that address number. But in C++, you don't have to know what you're doing. You just put an ampersand there and you say number. Okay. When scanf's called, it goes, finds the address number, and then plops what comes from the keyboard, it places it in what looks like the variable number. Okay. So we have to follow this rule of we're going to do this for RDI for the first one, and RSI will be this one which will be the address that leads inside this array. Everyone's still got this. Okay, next page, we'll carry out the goal there. Okay, so we left off back here. Okay, we had set up R15 to be the index and it's initialized to 0. So right now R15 is indicating this first 0 right there where the arrow is. It's indicating this cell. Okay. Ready? Let's see. I'm just thinking if we're ready for the loop. What is this? I think we can try. Okay, so top of the loop, CMP R15 with the maximum array size is R14. Okay, R14. If the index is greater than the number of quad words, we can't take any more data in. We're out of space. So jump greater or equal to done. If that this happens when R15 is greater than or equal to the size of the array. Okay, now let's suppose this is not true. If this is turned around that R15 really is less than the size of the array, then there is space available for one more number. And that's what we'll do down here. So we're going to start a setup for a block that scans in one float number from the keyboard and places it where we don't know which one it is, but one of these is R15. Maybe it's that one. Or wherever it is, that's where our numbers has to go. And remember, scanf over here doesn't want to know a 5. It wants to know one of these numbers that leads to that first byte in there. Okay. Ready? Let's I'm going to go slow because sometimes I forget, but let's start it out. First of all, there's no discussion about XMM here. RAX. 0 is how many XMM are involved? None. The next one is, here it is, RDI, first parameter. Move RDI, comma, money format. What is money format? It's pretty simple. It's that guy. Okay, the next one is where the complication comes in. We want to put in RSI, the address, the memory address of the cell of the array where we want the number to go. Okay, so what I'm going to do is, sorry, I'm going to do this. I'm going to take R15. This could serve as an example, which could be number 5. Okay, so let's move. Move means copy. RSI, comma, R15. No, we're not done. Okay, say that was a 5. And if I multiply by 8, then I'll have 40. And this is 8 plus 8 plus 8 plus 8 plus 8. 40 bytes after the start, we're at this byte. Multiply RSI by 8. And the reason for 8 is that each cell is a quad word. One cell of the array equals one quad word, which equals 8 bytes. Okay, so it's a number like 40. It would be the number 40 if we were trying to put it into cell number 5. If we were putting it into cell number 1, it would be a 1 times 8, which is 8, and that is 8 bytes later from the start over here. Okay, we're getting close. Now add RSI, comma, R13. R13 is that big address number. It's this number right below us here, in fact. And then we add 40 bytes over, and then we have the address number of the start of cell 5. That's really good. And it's in RSI. Is right there at that first byte of cell 5 in memory addressing form. So record that one. That's important. RSI is address of destination cell. Okay, not the index. That's different counting. That's these green numbers. This is the address counting, like these here, and we have it now in RSI. And here it is. Here's the prototype of scanf. One parameter for RDI and one parameter for RSI. We've got them both in place. They're both there. Right here and right here. Okay, so we can call scanf. Call. Okay, and then it pauses. You put some number, 37.49, and it will go into the array where the R15 register is. I can't write it in, it's too small. 17.5. Right there. Scanf has done its job, and after that number enters here, then the index should go 1 later. So we need to advance the index. R15. Okay. So now R15 is over here, waiting for the next number. Right. R15. So it's increased by 1. I think we're ready to repeat the loop. Okay, jump. Do it again. Okay, we'll put do it again here. With a colon at the end of it. That's important. So there we have a loop. Looping and getting numbers from the keyboard with each step of the loop. I guess this is the body of the loop here. And then it's bounded at the top by a compare and at the bottom by a jump back to the beginning. Anybody have a question? I'm pausing here for those recording it to get it all. No. Okay. Okay, I'm glad that I'm freely glad that you copy the whole stuff. That's okay. More important, I want that you understand why it's happening that way. It's one thing to copy stuff out of a catalog book, but it's another is to understand why it happens that way. Is that scanf is using memory addressing. Even in C++, when it says this, the ampersand returns a memory address of the variable number. Okay, we have to, that's the way scanf works. So whether we're calling it from a C++, like this statement right in front of us, or we're calling it from assembly like this statement, we still have to follow the rules of its prototype. And this will do it. Now we have, how's our clock doing? We're at 3 o'clock. I think we're fine. What? Just hold on a second. Did I? Okay. So there's one issue though. Let me see if. Oh no, yeah. We have to finish this. We were doing the function fill array. It started back here. Segment text, and there's its calling name, sometimes called the entry point. 16 pushes. Then comes this initial saving of the passed in parameters. Then we initialize a counter at 0. Then we fall into this loop and the counter gets incremented. And then when it's all done, it comes down. Where's the done? See, we're not done. Done. Call it. Okay. And when you come to done, let me think. Remember this fill array returns a number. Where's the prototype for fill array? Hold on, there it is. Fill array, its prototype says it returns a long integer. Read that as a 64-bit integer. That integer is how many numbers you put into the array. So, but we have it right in front of us. R15 has been counting numbers for us. And so we put a copy of it. That's like, let's pretend you entered 20 numbers. It's been accumulating in R15. Now we put it in RAX. And now we do 15 pop or 16 pops. And then we say return. In assembly, you just say ret, R-E-T. Okay. Why is this put over here? Well, for one reason is that in these 16 pops, there's a pop R15. It's going to lose its value if it stays in R15 and you come down here and pop R15. That nice number is lost. But if you look at the 16 pops, RAX is never popped. It's never pushed. There is no RAX in the list of pops, nor is there an RAX in the list of pushes. It's intentionally left out so that you can save a value in there, do all these pops, and it will still be there when you reach return, because the return will take the number in RAX and send it back to the caller, also in RAX. Okay. That's the end of this function. Well, almost the end. Everyone's got it? You want to ask anything? Okay. This is good as far as it goes, but class, there's one, we have to fix something. The something is, this array was declared for 25 numbers. What if you only have 12 numbers? See, here it is. It's being declared for 25. What if you only have 12 and you just want to enter your 12 and stop there? So we got to fix that one issue, and maybe, I don't know if that's do it today, or you got a lot to work on now. I also want to look at its neighboring function. let me- hold on. Its neighboring function is show array. So when this one goes back to here, then show array is to be called. Did I have? Where did we get? We did fill array. Where's? Okay. I'm going back to the manager level. In the manager level, you set up a block to call fill array. And here is that block, call fill array. And you save in R15 how many values are in the array. Okay. Let's finish the story here. Continue with fill manager. Okay. Manager just finished calling fill array. The array's got numbers in it. And how many numbers has been saved in R15? Okay. Now, manager wants to call show array just to visually verify everything looks good. Okay, so call, well, it's a setup. Set up to call show array. Okay. Show array, let's give it prototype. Its prototype is void show parentheses double comma long, and it's a size variable. Yes, okay, for size. Okay, knowing the prototype, you can go through the steps kind of blindly and just make a call to it. First one, there's no XMM here. RAX0. Next, the second parameter, the first real parameter is the array itself. And the array's name is, we're inside a manager. Manager created this array okay. And the third, not third, the second parameter is the size, but here it means the count of how many numbers went into that array. RSI, comma, and I have to find out where we left it. Oh, it's right here. When fill array is finished, it gives us the answer in RAX, and we saved it in R15. Okay, so R15 here. And that's pretty much it. Okay. Call show array. And it's a void function. There's nothing to do afterwards. And we're done. Okay. Okay, class. I've thrown a whole lot of stuff at you. This is all programming since an hour ago. What would you like me to repeat, or should I say more likely clarify? You digesting it all? Okay. You all got it. Okay. Copy it carefully, and you should be able to go home and, or maybe you're already at home. Key it in and make. Here's what you have tools to do. This is what we call assessor. SSOR. That's trivial. That's C++. Then there's manager. That's somewhat complicated. M-A-N-A-G. But you got to get two things here. You have to call fill and call show. You leave the rest undone. Postpone till later. Okay. And then fill over here. I gave it all to you on the previous pages except the part about ending early. I can tell you how that works, but I just want you to digest all this first. Okay, so I gave you all of this one, and then from there, manager is going to call show. And you should be able to get that much working from what I've given you on yellow pages today. Okay. There's some pieces to add later on. There's another module over here, but right now looks pretty good. No problem. Hoi Nguyen, you're okay. Do what you have to do. The loop just showed is in fill array. That's correct, Greg. It's that loop is inside of fill array. Okay. Here it starts. Fill array. I didn't do segment data and segment BSS, but here's segment text, and here's the name of the function, and it went down here through the blue ink, and then this green is a picture just for understanding's sake, and then the blue continued, and this loop in here is inside of fill array, and then when it reaches its max by this comparison statement, it then jumps out of the loop down to here, saves the number, pops out, and returns. That's all fill array. Okay. And show will also, oh, this is C++. You can do that one. Show, make a for loop that outputs one number per line according to the parameter size that's passed into it. Okay. Yes, assembly here can call C++ and pass the right parameters. It has to do a setup, just like always, and call C++ to output the values inside the array. Okay. Okay. All right. I can show you maybe I should save it or not save it. Here's what we're up against. That loop that I passed by is iterating. It's in the green box here. This loop is iterating, taking in a number and putting it into the array. What it doesn't account for is you have fewer numbers than the capacity of the array. Okay, so how do you handle that? Okay, I'll give you a brief preview, and then we'll redo it again next Tuesday, next class meeting. Okay, so here's what happens. You run a program that's asking for inputs, and it says, please enter a float and press enter. So scanf is sitting there waiting, and you can input something nice, 370.92. You press enter, and the scanf says the same thing. I mean, the prompt message comes up. Please enter a flow. And press enter. But instead of entering a float, you hold down the control key and press D, letter D. Okay, you can look it up somewhere in the ASCII non-printing table. Control D means end of inputs, end of transmission. Okay, so it has good meaning for us. Scanf is waiting for a number, but instead it gets Control D. And let me card here. What it does, it puts -1. Control D does this. It puts -1 in. Oh man, I hope I get the right register. The low half. I'm pretty sure it's RDX, not. Yeah, it's RDX. Uh-oh. RDX. Okay, so RDX ends up looking like this. Junk low half. Okay, so there's junk here. 1 0 0 1 1 1 0 0 1 0 1. This is just junk in the high half. The 32 bits at the low end are filled with -1. Do you know what -1 is in 2's complement? Everybody going to guess? -1. Oh, Greg, you missed it. No. Think real hard. 2 weeks ago, we did 2's complement. -1 is a screwy number. Long got pretty close, but he's still wrong. Okay. You're off by 1 digit, Long. So the answer is 1 1 1 1 1 1 in 2's complement. So this number in ordinary decimal arithmetic is -1. Okay. So here's how it works. You press Control D, and then I can't say that scanf puts it there, but your operating system detects a Control D and puts all ones in the lower 32 bits and leaves the junk up here. Got that? That's a signal that, I mean, it's an old signal. It's been there for 30 years. That Control D does that. Okay, our job is to check if we get all negative, if we get a -1 in there, and it's time to stop the loop. You want to get out of the loop. So how can you check for that? I recommend the following. CDQE. There's an instruction. RDX. Now remember, it takes only one parameter. And you can see C is convert, D is double, Q is quad, and E means in place. I don't know why it's E. I honestly don't know, folks. But it means don't use any secondary register. Just convert it here inside this one register. And the outcome is you get ones everywhere. So it takes the D is the double. This amount is a double word, and it extends it to a quad word, which is everything. Do a string search in the ebook, and it'll take you to a page where it sort of talks about that. But that's what it does. It takes what's in the lower 32 bits and just spreads it all the way through the whole thing. So this is RDX. Well, now you can compare RDX, comma, -1. If those two are equal, it's time to break the loop and get out. If they're not equal, you just iterate for another time. So the user who wants to stop after a small number of inputs into the array. We'll hold down Control and a D. And your loop stopping condition can include this, that if these are equal, then you're going to have a JMP to done, and you leave the loop. If they're not equal, you just continue straight below this. This is an if statement with no else. If it's true, these are equal, you're out of the loop. If they're not equal, you just continue asking for another number. Okay. I think I'm going to integrate that into this solution next time, but you see what's coming. There's two ways to stop the iteration. One is you reach the limit of the array. You don't have any more cells available. And the other is the user bails out. The user presses Control D. That interrupt puts all ones in the lower half. You extend it over the whole thing with this command. And then you check it to see if it's a -1. And if it is, there's your jump that gets out of the loop and you quit. Okay. This Control D mechanism needs a lot of explanation. We'll use it again and again as a way of signaling to the computer the end of something. Okay, that you're done with it. That's the way you do it. You know, in your TUFIX or WSL, you have a window where you input commands, and there's a prompt here. I forgot something $, and you input a command ls, and you can look at all the file directories or whatever. While that window is open, just hold down the Control key and press D. The window closes itself and says that person is done with me, so it must be the end, and it closes itself. Instead of clicking the little square up here, just try Control D on your terminal window, Control plus a D, and it'll close itself under the assumption that you're done with it. So Control D is a signal of something is finished, and the window knows how to respond to that. We're going to make our programs respond to Control D in the same way. Okay. Well, class, we ran. Where are we at? We're at 3:30. I want to pause here. I'll hang around to almost 4 if you want to ask me anything. I hope you have a long weekend with lots of peace and lots of quiet time, and you learn a whole lot of stuff. And then I hope that when you graduate, you get the 128K. That's 2 to the 7 times 10, 2 to the 10. That's 2 to the 17 power dollars per year. Okay. Have a nice afternoon, folks. I'm glad you were here.
Professor.
Yes, I'm listening.
So for computing the mean, so like how would you do that for that block? Would you do that inside the sum values file, or would you do it in the manager?
Yeah, here's what I suggest. To get the mean, the manager does the work. Manager calls sum.
And how would you call like the amount of so like the size of the or so like, to get the mean, you would do the total amount of
All the
like
numbers,
the sum, and then divide it by the
yes,
size of the array.
more
Or sorry, like
precisely.
the number of elements in the array.
Right, that last one is right. You divide by that number. So you
Like,
call
how would you do that?
sum. Oh, okay. Here, let's work through it right now. Some, I need a prototype. It's double, sum, double, array, long, and this is the count. Okay, so here it goes. Let's be formal. R0, move to RDI. Name of that is property. That's the array name. And move to RSI. Now the count, I think it was an R15. Call sum. Okay, now sum returns a double here. And so that number is going to show up in XMM0. Let's do it here. And what I want to do is save it in a safer place. Move SD XMM15, comma XMM0. Okay, so a notation says XMM15 is the summation of all the numbers in the array. Now we have to carry out the division. There's no function calling for the division. Oh, where is, oh, yeah. This, I forgot if this, let's take, this is the number of values in the array. We need to transfer that number. It's like 17. We need to transfer it to XMM so it becomes 17.0. Here it is. CVT SI to SD XMM. I'll pick on 14, comma R15. So CVT is convert. So this converts this integer number to this float number. And now we're set up for division. Div SD. We're going to divide 15 by 14. XMM 15 divided by XMM 14. There's that mean right there. The mean is now here. And this is all happening inside a manager. Take a screenshot.
Okay, thank you.
No problem. I'm glad to talk about it with you. Okay. There it is. Okay.
Professor,
Yes, I'm
I have another
listening.
question. So like in the block where you called fill array,
Yes.
so in the move RSI 25, so that gets set, is that like the def
Oh,
like
yeah, I know. That's that number has to match. Let me find it. The 25. I know what you're talking about.
Yeah.
That number has to match the size of the declared array.
oh, so that's just a declaration.
Yes, yes.
Okay.
Yeah, right here. That
Okay,
25 has to match the size of the array was declared for.
okay.
Uh,
And then that gets replaced by R15 when
yes,
after.
that's
Okay.
right. That's right. Okay,
Thank you.
no problem.
Professor,
Yes.
you have some questions in the chat.
Oh, okay. I'm catching up now. Okay, can you go over how to manipulate the 16R registers? Manipulate, yeah. How, now we have an array that accepts only floating point number. How do I handle user input of other characters such as letters? Ah, okay. Z Quang, that's a good question, but it's a half an hour discussion. I know, or it's a long discussion. What I suggest is this weekend, solve the problem where you assume the user inputs correct numbers. And next class meeting, I'll do the solution where the user inputs invalid numbers. Okay. Or you can go to the SI meeting this evening and they'll do it for you. When's that start? In about an hour and a half it starts. Tuan, manipulate the R register and the X and the XMM registers. See, we have a limited number of I'll call them commands. The experts would call them instructions for R registers. We can make a list right now. It's only like less than 10. You can do moves. You can do add, sub, mul, div. What else? I'll put convert on there, but actually convert. C, let's try again. CVT, SI, single integer, 2, single double. You can push and pop it. Push, pop. Now in the Intel user guide, which is a very thick book of 1,000 pages, they have about 100 of these. But in this semester, we're only going to learn about 40 or less, all total, for R registers and for XMM registers. Our grand total will be maybe 35. So if you're working with R registers, these are the only things you can do with them. Oh yeah, one more, increment. Then you can decrement an R register. I'm thinking hard. Is there anything else we can do with them? I don't know. Can't think of it yet. For XMM, the list is even shorter. You can move SD. You can do the for arithmetic, add SD, subtract SD, mul SD, div SD. You can't push or pop these. Oh, and there's square root. You can't do that one. You can't increment them. You can't decrement them. Oh, I know. You can do OR and XOR and AND on these R registers. Over here, it's kind of more complex. It's, I forgot it, or, I think it's or PD, XOR PD, and PD. P is for packed and D is for double. And these are not common. We use them once in a while. But I think that's about the whole list. So most of them require 2 operands. A few have 1 operand. These 2 right here require 1 operand only. I guess push and pop have 1 operand. Okay. All of these use 2 operands that I know of. All these use 2 operands, these 2 operands. So that's all we get is if you want to add 2 numbers together and they're integers, you have to say ADD R8 comma R12. You're adding R12 to R8. That's all you can do. If you're the convert is kind of strange. It's the only instruction that mixes one of the R registers with one of the XMM registers. It's kind of a one in the middle. CVT SI to SD, where you want the destination to be, MM9, comma R13. So it will take this integer over here and apply the bias rule and all the true exponent rule, and it will convert it from here to here. So this is one, I think it has a cousin, but this is the only one that mixes some R register with an XMM register. All the rest are independent of that. Okay, let me read the question here. Now we have an array that accepts only floating point number characters. Yeah, I'll have to do that next time. Basically, R registers do the storing part and XMM registers do the processing part. So we have to move store value in R. Yes, that's right. For our floating point numbers, you can store them in R registers. But if you want to process a floating point number, you have to move it over to here. This side is processing floats. You can store a float in one of these R registers, but if you try to do add or subtract with it, it won't. The machine won't recognize it as a float. It thinks it's some kind of integer. So it really doesn't work. You're going to sum together all those float numbers. You need them over here, okay, to make the addition work. So yeah, this is, you said it right in your chat message. This is processing of float numbers. You use these instructions. Temporarily, you can just, like the array, you can just store them in R registers, but they're not useful for any kind of calculating. So if I assume each register has their own function, not limiting it. Yeah, you're right. You're right. You're right. That's how it works. Okay. Yeah, the assembly keeps float numbers and 2's complement integers really separated. All these with SDs on it means the number has to be in IEEE format to do any good. And it has, and PD and PD. The numbers have to be in XMM registers, and yeah, that's correct, XMMs. And furthermore, they have to be in IEEE floating format. These numbers, if you're using these, it assumes everything is a 2's complement integer. Okay, we're We're all getting it. Okay.
Professor,
Yes.
can you remind me again, like when and why, do we call push keyword 0? Like, I'm not
Oh.
sure what the,
Yes, okay. If I can. It's kind of a messy page there. Let me first say, many times that keyword can be omitted, but there's 10% of the time it can't. We have push keyword 0. Okay. Or take this, for example, push keyword -1. Okay. The problem here is the push instruction doesn't know how to interpret this fully if you just said push -1. It looks at that and says, does the programmer mean 16-bit -1? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Does the programmer mean that one? Or does the programmer mean a 32-bit -1? Or does the programmer mean a 64-bit -1? I can't draw that many. There are lots of ones. So it's ambiguous to say this simply because the program doesn't know if you mean a -1 in the form of a word, 16 bits, or a double word is 32 bits, or a quad word, 64 bits. And so this is a, what do they call that? Qualifier. This qualifies this one. It's an adjective that describes what this is. And that's an adjective that describes what this one is. So if you say push quad word, push Q word -1, it's going to go for the biggest one, 8 bytes of -1. 8 bytes, 64 bits. If you said push, it's not common, but it happens sometimes, word 0, it's going to set up 16 bits of 0 and push that on the stack. Just 2 bytes. 2, 3, 4, 5, 6, 16 of these. 2 bytes only. Okay, that's what this would result in. So the Q word is giving a description to the push command, how many bits are involved when you say 0. Or if you said push Q word 37, it says form it as a number 37 that fits in a Q word register, a 64-bit register. Not so much in push, but there's a lot of other examples where you can omit Q word and the machine still figures it, the assembler still figures it out. I'm trying to think of one. I think the moves, I don't think anybody does this. Move RAX, comma, Q word 0. That would be saying, make sure you copy 64 bits of 0 into RAX. But you know, the assembler will figure it out anyway. So it's not necessary in that case. You can simply do this. And it understands that the destination is a 64-bit destination. Therefore, the programmer most probably wants 64 bits moved over here. Now, I'm really sure this is redundant, this piece right here in that example.
oh, I see. Thank you. Thank you so much.
You're certainly welcome. Certainly. still have enough R registers to store many values, which is what we have to push. Yes, Tuan. If you run out of R registers, what the professional programmers do is start pushing the extra data onto the stack. And it stays there until you need them. And then you have to pop it back out. It happens sometimes. But when you're done with the data in a certain register, reuse it. You don't always need 16 pieces of data at your disposal at every second of the program. At times, data will come and be used and disposed of, and new data arrives. But if you ran out of space, what they do is start pushing the extra values on a stack until it's needed. So how are you store more value than 16 space it has? Oh. Well, think of this. If you're in a long math equation, I can't think of an example, but if you're solving some analytic problem in assembly and you have a math equation that you have to get an answers to, and it's very messy. Maybe it's the evaluated polynomial of the 20th power. So Q of X is some coefficient X to the 20 plus 17, X to the 19 plus whatever stuff, 33, X to the 18. And you have to get a numeric answer for X equals 12. Okay. You probably will solve this one first and then push that answer. Solve this one second, push that answer. Solve this one third, push that answer. And you go all the way down the line to negative 16 X to the 0. You can solve that one and you put that on the stack. Now you have all those pieces of the polynomial. They're not in registers, but you've saved them on the stack. Now you take them out of the stack one by one and you add them up. See, there you need 20 values. You don't have 20 registers of any kind, R registers or XMM registers. So you push those on the stack. And then at the end, you can add them all up. There's an example of needing extra storage. Yeah, that's what happens. Okay, that's cool. I'm glad for you. Okay. Oh, yeah. Two. Yeah, I'm just not sure about the concept. Well, Tuan, keep working with it. It even me, I remember some years ago, it takes a while for it all to settle into your head. You keep working with it, and in eventual time, it will, all the puzzles of this, all the pieces of this puzzle will start to fit together. That's why I need to know the whole picture in deep to order to learn more. Yeah, I agree. We all as programmers need to know how things are working when we do them, not just we know what the outcome will be. We need to know how it works. And you're getting there. The fact that you're asking these questions makes me know that you're looking for solutions. I'm glad. Okay. Four. Four. Oh, April 4.
Thanks, Professor. Have a good week.
Thank you. You do the same. Take care of yourself. Okay, goodbye, everyone. I see you're leaving. I'm gonna leave too soon. I hope you got something out of today's long lecture. These get tiring. See you next week, everybody.